So remember that we've been talking about the parallax method. How far does parallax work for?
100 parsecs.
About 100 parsecs, okay? And it uses angles and things like that. We're going to go with a different technique to measure even greater distances. But first, we're going to review a few things about brightness and luminosity and that sort of thing. So, brightness and luminosity. What's the difference between those two things? So luminosity is how much energy the object is giving off, how much power it's radiating. Brightness is how much we receive. So one of the things that's been done astronomically is there's been scales that have been created to kind of compare the luminosities of objects and the brightness of objects, and those are called the magnitude scales. And there's two of them that you need to be aware of, and I think this is reviewed, so I'll go through it relatively rapidly. But apparent magnitude, which is represented with a lowercase m, is how bright an object actually appears to us. And this scale was created thousands of years ago, and originally it was a scale that only went up from 1 to 6. So the early astronomers, I don't know if this was in Greece or in Mesopotamia or in that area, somewhere in that area, they looked up in the sky and they said, oh, the brightest objects are first magnitude. And that one's a little bit dimmer, that's second magnitude. And that one's a little bit dimmer, that's third magnitude, all the way down to the dimmest things they could see, which they called sixth magnitude. Once we got technology that we could actually measure how much energy was coming from stars, we could actually determine that to go from first magnitude to sixth magnitude was about 100 times brighter. The sixth magnitude object was 100 times dimmer than a first magnitude object. And we did that with actual measurements. So if you do the math, there's 5 steps on the scale, and in order to get 100 times brighter in 5 steps, that means every step has to be 2.512 times brighter than the previous one, okay? So a second magnitude object is 2.5 times brighter than a third magnitude object. A second magnitude object is 2.5 times 2.5 times brighter than a fourth magnitude object, and so on, so on, so on, okay? So for example, the sun has an apparent magnitude of negative 26.7. Betelgeuse in the constellation Orion has an apparent magnitude of 0.5. So how much brighter is it? What do we do first? So what do we get? How we figure out how many steps away they are on the scale, how many steps apart. So how far apart are they on the magnitude scale? 27.2. So they have a 27.2 difference. And then what do you do?
Multiply. Or wait. No, you multiply.
You raise 2.5 to that power. 2.512 raised to the 27.3th power will tell you how much brighter it is, okay? So if you take 3 steps on the scale, you go 2.512 cubed, and it's 8 times brighter, okay? In this case, the sun happens to be like 76 billion times brighter than Betelgeuse, all right? And that's just how much energy we're receiving from the object. It's not really telling us how luminous those two objects actually are, which is what the second scale is all about, the absolute magnitude scale, represented by capital M. And this is a magnitude, a numerical representation or comparison of how bright objects would appear if they were all placed at the same distance, 10 parsecs away, okay? And it's a similar numerical scale. The smaller the number, the brighter the object would appear. And what does the absolute magnitude scale actually tell us? Okay, it gives an indication of actually how luminous the objects are. It takes away that distance component to making things be bright. So, for example, Alpha Centauri, closest star to us after the sun, is 4.3 light years away. It has an apparent magnitude of 0.1. It's pretty darn bright, okay? But its absolute magnitude is 4.5. It actually would appear quite, a lot dimmer if we put it 10 parsecs away. So it's similar to the sun in terms of its luminosity. And then Betelgeuse, on the other hand, which is 130 parsecs away, it has an apparent magnitude of 0.5. It appears dimmer than Alpha Centauri. It appears dimmer to us. But its absolute magnitude is negative 5.16, so it's actually 10,000 times more luminous than Alpha Centauri, even though it doesn't appear that way. So the absolute magnitude scale gives you an indication of their actual luminosities of the object. What's that? So this is the equation, you guys, that's in your data booklet that looks at the differences in magnitude, and you can use that to find how far away something is. So if you take the difference in apparent magnitude and absolute magnitude, that's equal to 5 times the log base 10 of the distance divided by 10. That's the equation in your data booklet. If you use this equation and solve for d, you'll get the distance to that object in parsecs. All right? It requires a little bit of mathematical manipulation, though, and you need to understand logarithms a little bit. So why don't we go through that? Ultimately, you'll end up with this bottom equation, but that's not what's in your data booklet. So, okay, so please, the other thing to be really clear about is that these magnitude scales, you guys, they are a measure of the star's brightness or a measure of the luminosity. They don't actually tell us the brightness of the luminosity, because brightness would be how many watts per square meter we're receiving from the object. It wouldn't be, if I say it's an apparent magnitude of 3, that doesn't tell me that it's 3 watts per square meter. It's just a relative kind of measurement. Just like temperature. Remember when we were dealing with temperature earlier in the year, and we said that temperature is a measure of the average kinetic energy of the molecules? So 76 degrees doesn't mean how much energy those molecules have. It's just a measurement of that energy. Same thing with magnitude. It's a measurement of the brightness when we talk about apparent magnitude, and it's a measurement of the luminosity when we talk about absolute magnitude. Okay? All right. So absolute magnitude, let's see, we just went through that this way. Okay, 4 questions. You got 2 stars, you know their apparent magnitudes and their parallax angle. Which star is closer? Okay, so 2 is closer because it has a greater parallax angle, right? Everybody in agreement with that? Feeling good? Which star appears brighter? Oh, 2 or 1?
Wait. Oh, 1, yeah, 1.
1 appears brighter. It has a smaller apparent magnitude, a smaller numerical value for its apparent magnitude. Therefore, it appears brighter. Okay? Which star is actually more luminous?
2.
And what makes you say 2?
Because the parallax angle is 3 times greater from star 1 to star 2, but the change in 1 unit from apparent magnitude, 1 equals 2.512 times greater, so therefore star 2 must be more luminous.
Okay. Everybody in agreement? Star 2 is more luminous? Which one appears brighter?
1.
Which one's farther away?
Star 1. Oh, okay.
If it appears brighter and it's farther away,
Then it's
it has to be more luminous. Okay? Okay? Does that make sense? Okay? Which one would have a greater absolute magnitude? Let's rephrase this question. I don't think it's worded very well. Which one would have a greater numerical value for absolute magnitude? 2 would. The numerical value of its absolute magnitude will be a larger number because it is a less luminous object. Okay?
So confusing.
I agree.
So confusing.
I agree. Okay, let's try these 3. 2 new stars, 3 new questions. Which star is farther away?
3.
And why do you say star 3?
Smaller parallax.
Smaller parallax angle. Okay, we'll go with star 3. Which star is more luminous?
3.
Because it's farther away?
The same.
It has the same what?
Absolute magnitude.
I'll say the question again. Which one's more luminous? They are the same. They are the same. Remember, absolute magnitude is their luminosity. So it is the same. Okay?
It's really confusing though, because the last question.
So the next technique that we're going to then get into is basically comparing brightnesses and luminosities of objects to figure out how far away they are. And the reason this works is purely because of geometry, right? You imagine a light source. It could be a star, it could be a light bulb, or whatever. It's giving light in all directions. The farther away you get from that object, the greater area that energy or that light is spread out over. And it increases with the square of the distance. This is known as the inverse square law. So notice if I get 1 unit away, there's 1 square that this light is spread over. If I go 2 units away, it's spread over 4 units. And if I go 3 units away, it's spread over 9 units. So the area over which the energy gets dispersed increases with the square of the distance. And this is why we have so many equations that have an inverse square relationship. Think about gravity, gmm over r squared. Think about electricity, kqqq over r squared. Okay? Things that spread out uniformly in all directions will get weaker with the square of the distance. So we can use this in astronomy to measure how far away things are if we know 2 pieces of information. If we know how bright the object is, which is easy, we just observe it and measure it. But then if we can figure out how luminous it really is, we can calculate how far away it is. And this is that relationship is what we will do to measure greater distances. It's comparing apparent brightness to luminosity and looking at this relationship. But the brightness, the energy we receive, the brightness of the object will equal the luminosity, how much energy it's giving off, divided by the surface area of the sphere that energy is spread over, which is 4 pi d squared. Does that make sense? So if we're going to use this relationship to measure distance, then the critical thing to know is luminosity. How do we figure out how luminous a star is if we can't go to that star and actually like measure it? You know what I mean? How do we determine it? And there's a couple different ways. So the first way that we measure luminosity is by looking at the spectra of the star, the spectrum of the star, okay? And this is a technique called spectroscopic parallax, which is another, we can call this stupid too. This is a stupid name because parallax is not involved at all, okay? There's no trigonometry, there's no angles, okay? So you'd be really clear that when we're talking about distance techniques, there's parallax, which uses the angles of the wobbling stars, and then spectroscopic parallax, which doesn't have anything to do with parallax at all, okay? Instead, we look at the spectrum of the star, we find its temperature using Wien's law. Remember, the peak wavelength can determine the temperature of the star. Then, when we know its temperature, we know what spectral class it is. We can put it on the HR diagram, and remember the vertical axis on the HR diagram is luminosity, so we can find its luminosity. Huh. Awesome. So this technique is relatively useful, and it extends our reach a little bit. Remember, parallax only went out to about 100 parsecs. Suddenly we have a technique that we can measure distances out to 10 million parsecs, 30 million light years, okay? We're leaving the Milky Way galaxy now and measuring distances to nearby galaxies, okay? I believe this limit, why is it limited to only 10 megaparsecs? Well, I think at some distance you can't isolate individual stars anymore and measure their spectra. So I think that's probably the limit for this technique. But it reaches out much farther than parallax does. Parallax is just working into like our neighborhood of the Milky Way galaxy. Now we have a technique to measure distances to nearby galaxies if we want to. Okay, just to review, Wien's law again allows you to calculate the temperature. If you know the peak wavelength of the black body spectrum of the object. And then Stefan Boltzmann's law talks about luminosity of an object in area. Now, this is one of the things you can do with Stefan Boltzmann's law now is if you know the temperature of the star and you know how luminous it is, you can now calculate the size of the star, its surface area. And then if you remember 4 pi r squared, you can calculate its radius and all that fun stuff if you want to. Okay, so that's something that you can do with Stefan Boltzmann's law. All right. Now, there are other techniques for finding luminosity. And these are other things that we've used to kind of verify this technique and verify parallax. And the first other technique that was used was these stars called Cepheid variables. They're very special stars. They were first discovered in 1784 in the constellation Cepheus, so we call them Cepheid variables. Couple things to remember. A variable star is a star that doesn't stay continually bright. If you observe it for a while, it gets brighter and then dimmer and brighter and dimmer over time. It'll oscillate, bright, dim, bright, dim. There are different ways that can happen. We talked about binary stars that do that. If you have an eclipsing binary and one star goes in front of the other one, its brightness will change. This is a special type of star that actually gets brighter and dimmer. It's kind of, I don't want to say pulsing because you'll start thinking of pulsars. It's not a pulsar, but it's a star that it expands and gets brighter and then contracts and gets dimmer, and then expands and gets brighter and contracts and gets dimmer. And it just does it on a very regular cycle. When you discover one of those, it's very, very useful in terms of astronomy, because what was found is that the period, the time they take to go bright, dim, their period of oscillations is related to their luminosity. So when you find a Cepheid variable somewhere, you watch it over time and you see how long it takes to go bright, dim, and that tells you how luminous it actually is. I don't know why exactly. It has to do with nuclear reactions and the size of the star, but they've been able to figure that out. And so when you find a Cepheid variable, you know its luminosity, you measure its brightness, boom, you measure how far away it is, okay? So when these stars were discovered and when it was figured out that we could calculate their luminosity, we were then able to measure distances using them. And this is a technique that goes out a little bit farther. Now we go out to about 60 million parsecs, 180 plus million light years, okay, maybe about 200 million light years. So we're getting farther away now. This type of star was the star that made Edwin Hubble famous for one thing. He got famous for other things as well, but you've heard of the Hubble telescope. One of the things that Hubble discovered is that the Andromeda Nebula was an actual galaxy outside of the Milky Way. Back in the early 1900s, this fuzzy patch in the constellation Andromeda was just a fuzzy patch. We called it a nebula, and there was big debate. Is it within our Milky Way galaxy, or is it beyond? At that point, pretty much most astronomers felt that the Milky Way was the universe. There wasn't anything beyond. But Hubble, and actually it was one of his assistants, found a Cepheid variable in the Andromeda Nebula and measured its luminosity and measured its brightness and measured the distance and found it to be about 2.5 million light years away, which was much, much, much farther away than anything in the Milky Way galaxy, and therefore it was the first piece of evidence that other galaxies existed. And that was huge. That was a huge discovery. This concept of a standard candle, that's a term you need to be familiar with. A standard candle is anything that we know its luminosity so we can measure its distance. As soon as we discover the luminosity of an object, we call it a standard candle. We use it as a standard candle because we know its luminosity, we measure its brightness, and then we measure its distance. So Cepheid variables were some of the first standard candles. Now we have other objects in the universe that we can use as standard candles. And one of the more famous ones and more useful ones are a very special type of supernova. We've talked about supernova explosions. It turns out there's different kinds of supernova explosions, and one of them is called a type 1a supernova. These are really great for measuring really far away because supernovas are so bright. And these, when this particular kind of supernova happens, they reach a certain brightness, and they are a certain amount of they have a certain amount of luminosity that we know. This was a technique that was used very recently for these two different groups of astronomers that discovered some really important things about the expansion of the universe, and I'm pretty sure they just won the Nobel Prize for it, maybe last year or the year before. So really good technique. And again, okay, so type 1a supernovas are very useful. There are other things that can be used as standard candles. For example, some types of galaxies. There's certain types of galaxies that astronomers have figured out how luminous they are, certain types of spiral galaxies and things. And if you discover one of those, you're like, oh, this is how luminous it is, this is how bright it appears, I can calculate how far away it is. To go even farther away, to measure the farthest distances in the universe, there's a whole different technique that we'll talk about more in our next unit. But basically, it looks into the fact that the universe is expanding, and the farther away an object is, the faster it's expanding away from us. And we can look at that and measure, therefore, its redshift. We can find a really distant object, calculate from its spectrum how fast it's receding from us, and then determine how far away it is. And this is a technique that's used for really distant objects. And so that's our final distance measuring tool.
We need to know these things.